Okay, right. So I hope you are all doing well. Before we dive into today's main topic, let's quickly recap our previous concepts. Can someone tell me the difference between heat and temperature? Already you know that del Q means heat, del T means temperature. Yeah. So, what is the difference between heat and temperature? Yes. So, heat is the energy. Yeah. Heat is a energy transferred. Temperature is a measure of the average kinetic energy of the particle. So, measure of average kinetic energy of that particles. Okay. They are related, but not the same. Okay. Right. Now, let's start with a thought provoking question that leads us into today's topic. Imagine you have 1 kg of iron, okay, and 1 kg of water. So, kg means mass, yeah. So, you have 1 kg of iron and 1 kg of water. Clear? Okay. If you apply the exact same amount of heat, Q, same, okay. If you apply the exact same amount of heat, say for example, we can take 100 joule, yeah, to both substances. Which one do you think will heat up faster? Which one do you think will heat up faster? So meaning show a larger increase in temperature. And why? Because the ion will heat up much faster. Yeah, already you know that. The ion will heat up much faster because different materials react differently to the same amount of heat. Okay, again I will say that different material react differently to the same amount of heat. So this difference is precisely what we are going to explore today with the concept of specific heat capacity. Clear? Okay, right. So let's quickly test your fundamental knowledge with a short 3 question MCQ about heat basics. Okay, I will share the screen. You can see that MCQ. Yeah, clear? Right. So first to one word. First one, which is the primary difference between heat and temperature? Which is the primary difference? Good. Yes. What is the primary difference between heat and temperature? Already I told you that. Yeah. Yes. Option 2. Heat is the energy transfer due to temperature difference. But the temperature is the average kinetic energy per molecule. Yeah. Right. Right. This is a option 2. Okay. This is the answer for the first question. Now, second question. Very easy one. Simple one. The SI unit of heat energy. Option A, Kelvin, Joule, Watt, Newton. Which one is correct? Kelvin, Joule, Watt, Newton. Kelvin, Joule, Watt, Newton. Which one is the SI unit for heat energy? Any answers? Already I told in that class, if you supply a amount of heat, we can take 100 joule. So 100 is a numerical value. Joule is the unit for the heat energy. Yeah. So option B is the correct answer. Joule. J. Clear. Third one. Which of the following best describes heat transfer by conduction? Already you are familiar with the conduction, convection, radiation. Yeah. This is a form of heat transfer. Okay. So according to the conduction, which of the following best describe heat transfer? Option A, heat moving through electromagnetic waves without medium. Electromagnetic waves. Okay. Option B, heat transfer to the bulk motion of fluids. Option C, direct transfer of kinetic energy through molecular collision in a solid or stationary fluid. Clear? And fourth one, heat absorbed or released during phase change at constant temperature. Which one is correct? Option A, B, C, D. Which one is correct? Yes. So, according to the conduction, direct transfer of kinetic energy through molecular collisions in a solid or stationary fluid. Yeah, option C is the correct answer. So, we can check the answer. Okay. First one, heat transfer due to the temperature difference, and temperature is the average kinetic energy per molecule. Second one, SI unit of heat energy, joule. And the third one, which of the following best describe heat energy, heat transfer by conduction? Direct transfer of kinetic energy through molecular collisions. Yeah. So in a solid, there are millions molecules there. Okay. So molecule, if you get that, if you heat that substance, it will get energy and their vibrations high. Yeah. So the direct transfer of kinetic energy through molecular collision in a solid is the correct answer. Clear? Okay, right. So today we are defining three closely related but distinct ways to measure how a substance handles heat. Okay, how a substance handles heat. Let's start with the broadest concept. First one, heat capacity. Heat capacity. Capital yes. So heat capacity formula, S is equal to del Q by del T. Yeah. So definition, this is a, that is a heat capacity. This is a amount of heat required to change the temperature of an entire substance by 1 unit. It depends on the size and mass of the object. It depends on the size and mass of the object. So, heat capacity is the amount of heat required to change the temperature of an entire substance by 1 unit. Okay. So, if you have any liquid or a solid, if you want to increase 1 unit temperature change, yeah, you have to give heat, yeah. So that amount of heat required to change the temperature by 1 unit, for example 0 to 1 or 1 to 2, 2 to 3, that like that. Okay, so that is a heat capacity. Clear? And units, heat energy joule, temperature Kelvin. Yeah. So joule per Kelvin, joule per Kelvin, joules per Kelvin. Okay, clear? Okay. Next one, specific heat capacity, small s. Specific heat capacity, small s. Okay. So formula S is equal to 1 by m into del q by del T. Same formula, but only one time involved here, that is this time 1 by m. This is small s, okay? This is small s, not a capital S. Capital S means heat capacity, small means specific heat capacity. So this is a heat capacity normalized by the mass of the substance. Normalized by the mass of the substance. It is a characteristics constant for a given material. That is, specific heat capacity is a characteristics constant for a given material. And it is independent of the sample size. It is independent of the sample size. It represents the material thermal inertia. It represents the material thermal inertia. Clear? Okay. So again, unit, SI unit here, joule, Kelvin, but here also mass is there. So kilogram, Kelvin, joule per kilogram, joules per kilogram per Kelvin. Clear? So this is the specific heat capacity normalized by the mass. Heat capacity normalized by the mass. So that's why we can put 1 by m. Clear? Okay, right. So next one, molar specific heat capacity. Molar specific heat capacity. So already you know that that term mole, okay, mole, molar, like that. So third one, molar specific heat capacity. Molar. So this is capital C. Okay, this is capital C. So this is the heat capacity normalized by the number of moles. Already you know that in the specific heat capacity normalized by the mass. But this is normalized by the number of moles. Number of moles means mu. Okay, number of moles mu of the substance. So this links heat capacity to the internal atomic and molecular structure. So we can write the equation for the molar specific heat capacity. C is equal to 1 by mu, and again same equation as the previous one. Yeah, del Q by del T. That's it. So here also unit joule, where mu unit for mole, mole dot Kelvin. Clear? Joules per mole per Kelvin. So now that we have the definition, let's explore two key details. Let's explore two key details. First one, specific heat of water and the calorie. First one, we are going to explore the two key details. First one, specific heat of water and calorie. Okay, calorie. Okay. Water has an exceptionally high specific heat capacity. Water exceptionally high heat capacity. Okay, high specific heat capacity. So small s equal to the value for water 4186, and unit already you know that joule per kilogram dot Kelvin. Very important one word, specific heat capacity of the water 4186, 4186 joule per kilogram Kelvin. This means water can absorb huge amount of heat energy. Okay, amount of that is, water can absorb a huge amount of heat energy with only a small rise in temperature. making it a fantastic thermal regulator in nature and industry. Okay, so for a small rise in temperature, you have to give the huge amount of heat energy like that 4186 joule per kilogram Kelvin. Okay, right. This property of the water also lead to the historical definition of the unit calorie. Unit calorie, CAL, calorie, CAL. Yeah, 1 calorie was precisely defined as the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Okay, so 1 calorie was precisely defined as the amount of heat required to raise the temperature of 1 gram 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. This is a definition for 1 calorie. Note it down. Very important short answer. Okay, 1 calorie. So 1 calorie is a definition the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Okay, so you have water has a mass, that is in gram. 1 gram of water, we can take the 1 gram of water, temperature 14.5 degrees Celsius. So if you want to increase the temperature to the 15.5 degrees Celsius, you have to give the amount of heat. That amount of heat is known as the 1 calorie. 1 calorie. Clear? Okay. Next one. Second one. B. Theoretical molar specific heat for solids. So C is approximately 3R. C approximately 3R. Theoretical molar specific heat for solid. Okay. For most solids at ordinary temperatures, theory predicts very simple value for the molar specific heat capacity. So this prediction is based on the law of equipartition of energy. Okay, this is based on the law of equipartition of energy. Clear? Okay. For most solid at ordinary temperatures, theory predicts a very simple value for the molar specific heat capacity. This prediction is based on the law of equipartition of energy. Okay. So this law states that total energy is equally divided among all the possible degrees of freedom. Each degree contributing 1 by 2 kT of energy per molecule. Okay. So in a solid, each atom acts like a simple harmonic oscillator and has 6 degrees of freedom. 3 for kinetic energy and 3 for potential energy. Already you know that. Yeah. So law of equipartition of energy means this law states that total energy is equally divided among all the possible degrees of freedom. Each degree contributing 1 by 2 of kT of energy per molecule. Okay, right. Applying the equipartition law, the theoretical molar specific heat capacity for solid works out to be approximately 3R. Okay, 3R. Here R means universal gas constant. Universal gas constant. This value is about 25 joule per mole dot Kelvin. So R is a universal gas constant. This value is about 25 joule per mole dot Kelvin, right? So you have to know this theoretical molar specific heat for solid C is approximately is 3 times the universal gas constant. So 3 times the universal constant means 3 into 25 for approximately. Okay, so 25 joule per mole Kelvin. Clear? Okay. So these are all for molar specific heat capacity, and heat capacity, and the final one that is calorie, and for water 4186 joule per kilogram Kelvin. Yeah. Okay. Right. Now we are going to see the process of finding the specific heat capacity of the solid. Okay, finding the specific heat capacity of the solid. I will share the screen. You can see the one simulation. One second. Okay, good. Okay, right. So specific heat capacity of the solid and liquid. Now we are going to finding the specific heat capacity of the one solid. Okay, right. So this experiment, which is used to determine the specific heat capacity of both solid and liquid using the method of mixtures. Method of mixtures. The core principle for this entire experiment is the principle of calorimetry. Okay, the core principle for this entire experiment is the principle of calorimetry, which is said that for an isolated system, heat lost by the hot body, sorry, heat lost by hot body is equal to heat gained by cold body. Okay, this is a principle of calorimetry. Heat lost by hot body is equal to the heat gained by the cold body. Yeah, correct? Okay. So here you can see that one copper calorimeter with the lid, okay, and a stirrer, insulating cover, beaker, thermometer is there, okay, weighing machine, okay, right. Here, first of all, we have to ensure our weighing machine has no zero error, okay. First of all, we have to ensure the weighing machine has no zero error. Clear? Okay. So here 0, 0. Okay. Correct. First, weigh the clean, dry, empty calorimeter with its lid and stirrer. 40 gram. Okay, 40 gram. This is a weight of this is a mass of the calorimeter without water. We can take as M1. Clear? Right. So the type of calorimeter here, copper. Clear? Okay. Now pour an adequate amount of water into the calorimeter. Now you can note down the weight increased. Yeah. The weight of the calorimeter with the water. Notice that 90 gram. Okay. Noting this as mass M2. Okay. Noting this mass as M2. The mass of water means M2 minus M1. Before M1, now M2. So M2 minus M1, we will get the mass of the water. Correct? Okay. Now place the calorimeter in its insulating cover. So we have to open the insulating cover like that. Okay. And put that calorimeter in that insulating cover. Clear? Okay. Now put the thermometer inside the cover. So initial temperature of the liquid is 25 degrees Celsius. Okay. We can take this temperature as T1. So we have M1, M2 and T1. Clear? Okay. Right. Now next. So here you can see that one solid cylinder. Clear? So we have to finding the mass of that solid cylinder like that, 20 gram. Okay, the weight of the solid cylinder and mass here M3. We can take this mass as M3. Okay, right. Now tie a strong non-flexible thread tightly around the middle of the solid like that. Clear? Okay. Suspend the solid in a beaker of water here like that. Suspend the solid in a beaker of water placed on the tripod stand. Crucially, the solid must be completely submerged. Okay, at least 0.5 centimeter below the surface. So this ensures the metal reaches the same temperature as the water on heating. Okay, boil the water with the Bunsen burner. Boil the water with a solid suspended for about 5 to 10 minutes. So this allows the solid to reach thermal equilibrium with the boiling water. Yeah, this allows the solid to reach the thermal equilibrium with the boiling water. Measure the temperature of the boiling water. Temperature up to which solid is heated, T2 is in degrees Celsius. Okay, measure the temperature of the boiling water. This is a solid's initial temperature. We can take it as T2. Now we have a T2. This is a solid's initial temperature. Now we must be quick. Remove the solid from the boiling water by holding the thread. Okay, right? So now open that lid. Okay, cover. Now take that. Clear? Okay. Shake off any sticking water and immediately place into the water in the calorimeter. Okay, right. So close the lid and continuously stir the water like that. Continuously stir the water. Stirring ensure the uniform distribution of temperature. Uniform distribution of temperature. Okay. Right. Okay. Now results. So specific heat capacity of the calorimeter kilogram, kg inverse, k inverse, okay, mass of the solid, and we have to fetch the data, right? So here you can see that specific heat capacity of the calorimeter 0.386, mass of the solid 20 kilojoule, like that. And the specific heat capacity of the water 4186, already you know that, okay, result. So the final temperature of the mixture 26.62 degrees Celsius, and the specific heat capacity of the solid 0.38 kilojoule. Correct? Okay. So applying the principle of calorimetry, heat lost by the hot body to the heat gained by the cold body. When you place the hot solid into the calorimeter, the solid loses heat and the water and the calorimeter gain heat. Okay, right? So, and measure the temperature. This is the T3, okay, final constant temperature of the mixture, T3. So, the solid loses a heat and the calorimeter and the water gains that heat. Okay. So we have a formula that is M3 SO T2 minus T3. Okay. M3 SO T2 minus T3 equal to M2 minus M1 SW T3 minus T1 plus M1 S1 T3 minus T1. This is a formula to find the specific heat capacity. Okay. Now we have the formula. Yeah. Here M3, mass of the solid. M3 means mass of the solid. SO, specific heat capacity of the solid. What we are solving for? Yeah. Okay. So SO, okay, or S0, you can take anything, okay, S0, okay. So specific heat capacity of the solid, okay, M3, mass of the solid, T2 minus T3, change in temperature of the solid. Already we know that T1, T2, T3, yeah, T3 is the final temperature, okay, T1 is the initial temperature, T2 is already you know that in that threat condition, yeah. So T2 minus T3, which gives change in temperature of the solid. M2 minus M1, mass of the water. Already I told you, yeah, M1, okay, M2. So if you pour the water into the calorimeter, we have a mass. So M2 minus M1, which gives the mass of the water, okay. SW. So SW means very simple, specific heat capacity of the water. Already we have a value, known value, yeah, 4186, okay. So SW, specific heat capacity of the water. And already you know that T3, T1 like that. M1 means mass of the calorimeter. Mass of the calorimeter. Okay. S1 means specific heat capacity of the calorimeter material. That is known value. Yeah. If you choose copper or aluminum, we have a value. That is specific heat capacity of that material, which is also constant. So S1 means specific heat capacity of the calorimeter. Calorimeter, water, of the solid to we are solving for. Okay. T1, T2, 3, T3. Already you know that. M1, mass of the calorimeter. M2 minus M1, which gives the mass of the water. M3, mass of the solid. Okay. Clear? Okay. So by rearranging the equation, we can calculate the SO, that is the specific heat capacity of the solid. Okay. By this simulation, by this experiment, we can calculate the specific heat capacity of the solid in the laboratory environment. Okay, clear? Okay, right. So this is a very important simulation. Okay. So understanding the formulas is key to solving problems. Let's work through two numerical examples together. I will share the screen. to show the problems. Once again, I will share the screen. So this is the first problem, problem number 1. Basic application of specific heat capacity. How much heat energy is required to raise the temperature of 2 kg of water from 20 degrees Celsius to 80 degrees Celsius? So specific heat capacity of water, already you know that, small s, 4186. Okay. How much heat energy is required to raise the temperature of 2 kg? So water 2 kg from 20 degrees Celsius to 80 degrees Celsius. Clear? Okay. So we have the data. First of all, what is the formula to find the heat required? Already you know that. Yeah? Yes. Good. This is the. So in this sum, we have to find the required heat. So del Q M del T goes there. So M, yes, del T. Clear? Okay. Mass. We have a 2 kg of water. Okay. 2. Specific heat 4186 joule per kilogram dot Kelvin. Temperature change. So this is a temperature change. So temperature change means final temperature minus initial temperature. Yeah. In this case, final temperature 80 degrees Celsius, initial temperature 20 degrees Celsius, which gives 60 degrees Celsius. Okay, which gives 60 degrees Celsius. Okay. A change in 1 degree Celsius is equal to change in 1 Kelvin. Okay. Change in 1 degree Celsius is equal to change in 1 Kelvin. So we can take as 60 Kelvin also. 60 Kelvin also. Okay, this is a T. Okay, now put that value here. Put that value here. 60 Kelvin. Okay, right. 2 into 4186 into 60, which gives del Q 502320 joule. The heat energy required is 502320 joules. Okay, this is a final answer for this first sum. 502320 joules. Clear? Okay. Now we are going to discuss the second problem. I will show the screen to show the problem number 2. This is a problem number 2. Okay, molar specific heat capacity calculation. A 0.5 kg sample of metal, molar mass 27 gram per mole, requires 10,800 joule of heat to increase its temperature by 20 Kelvin. Calculate the specific heat capacity S of the metal and its molar specific heat capacity C. Already we know that C is approximately 3 times of the R. So 3R. So 3R. Here you can see that the value approximately 24.94 joule. Already we know that 25. Yeah. So 24.94 joule per mole Kelvin inverse. And universal constant value 8.314. Okay. Clear? So 0.5 kg sample, molar mass, joule, that is heat energy and temperature. Okay. So in this sum, we have a data. First of all, formula, that is 1 by m del q by del t. Yeah. Del q 10,800 joules. M 0.5 kilogram. Del T 20 Kelvin. Clear? Okay. So yes. 10,800 joule per mole, 0.5 kg into 20 Kelvin. Clear? So 0.5 into 20, which gives 10. Yeah, 10. So 10,800 by 10 Kelvin joule. So 0 cancel, which gives 1080 joule per kg Kelvin. This is a specific heat capacity. Okay, this is a specific heat capacity of that metal, 1080 joule. This is a part number A. Now we are going to discuss the part number B, that is molar specific heat capacity, that is C. Okay, so already we know that the relationship between the S and C, yeah, S and C, that is the relationship between the S and C. C is equal to S into M. This is molar specific heat. This is already you know that specific heat capacity. Yeah, specific heat capacity. This is the molar mass. This is a molar mass. Okay, right. So before we get into the sum, we have to convert the molar mass to SI unit, kilogram per mole. Okay, molar mass to kilogram per mole. This is a SI unit. So we have M is equal to 27 gram per mole. So which gives 0.027 kilogram per mole. Okay, 27 gram per mole in our sum. So which is equal to 0.027 kilogram per mole. This is a M value. Already we have a S value. Now we have a M value. Just put in that formula. We will get the C. That is molar specific heat capacity. Clear? Okay. C equal to 1000 joule per Kelvin, kilogram dot Kelvin, 0.027 kilogram per mole. Yeah. So which gives 29.16 joule per mole dot Kelvin. Clear? This is a molar specific heat capacity, 29.16. So this value is very much close to the theoretical value, 3R. Already we have a 3R value, and that is 24.94. Yeah, joule per mole Kelvin, according to our sum. So confirming it behaves like a typical solid. Confirming it behaves like a typical solid. Clear? Okay. So let's quickly wrap up this part with a 5 MCQ. I will share the screen again to show the 5 MCQ. Okay, get ready. So you have a 5 minutes to. Okay, right. 5. First one. What is the SI unit for specific capacity? Yes. What is the SI unit? So here joule Kelvin inverse, joule mole inverse, Kelvin inverse, like that. Okay. In Google form, we don't put -1 as a superscript. We have to put like this, right? So that's all. That's only here you can see that joule kg inverse, Kelvin inverse, joule mole inverse, Kelvin inverse. What is a SI unit? What is a SI unit? SI unit for specific heat capacity. Okay. So already I told you that is joule. Yeah. Yes. Yes. Joule per kilogram Kelvin. So joule kilogram per Kelvin dot means joule kilogram inverse Kelvin inverse. Yes. Option C is the answer. Okay, good. Second one, the molar specific heat capacity C of the most solid at ordinary room temperature is theoretically predicted to be equal to 5 by 2 R or 3 by 2 R, 3 R, R. Already R means universal gas constant. You know that, yeah? So molar specific heat capacity of the most solid at ordinary temperature, theoretically, approximately to 3R, R, 3 by 2 R, 5 by 2 R. Which one is correct? Which one is correct? Yes. Yes. Okay. Okay, right. So 3R. Clear. Okay, right. So third one, the heat capacity S of the substance. The capital S. Yeah. So the capital S means independent of the mass of the substance, proportional to the number of moles, proportional to the mass. Already one response is there. Yeah. Option C is the answer. Yes is related to the mass of the substance. Yeah. Right. Fourth one calorie is defined as the amount of heat required to raise the temperature of 1 gram of water from which one is to which one? 0 to 1 degree, 99.2, 100, 14.5 to 15.5, 20 to 21. Which one is correct? 1 calorie. Defined as the amount of heat energy required to raise the temperature of 1 gram water from. Yes, option C is the correct answer. 14.5 degree to 15.5 degree. Yes, correct. And the final one, according to the law of equipartition of energy, the theoretical molar specific heat capacity, that is C, 3R for a solid arises from the assumption that the internal energy is primarily due to the translation kinetic energy or rotational kinetic energy, potential energy, or and the final one, vibration energy of the atoms. So according to the law of equipartition energy, C is approximately 3R is primarily due to the both energy of the atom, vibrational energy and that is kinetic and potential energy of the atom. Okay, we can see that answer. So first one, SI unit of specific heat capacity, joule kg inverse, Kelvin inverse. Already you know that C is approximately 3R. Heat capacity, yes, proportional to the mass of the substance. Okay, and the final, fourth one, 14.5 to 15.5, and the final one, primarily due to the vibration energy, kinetic and potential energy of the atom. Clear? Okay, good. So these are all for today. Now just note the homework sums. This is your homework sum. One theoretical, one numerical. Just note it down. If you have any doubt, please ask me via the chat box, or you can unmute yourself. So this is the all belongs to specific heat capacity. Today we know that specific what is heat capacity. Yes, capital S, molar heat capacity C, universal gas constant R, and C is approximately 3R. Yeah, okay, clear. And for water 4186, remember that value, very important value. To homework question conceptual, explain why the specific heat capacity of the solid is nearly constant at room temperature but decrease significantly at very low temperature. Okay. Numerical, a substance with a molar mass 0.050 kilogram mole inverse has a specific heat capacity of 1000 joule kg inverse Kelvin inverse. Calculate its molar specific heat capacity. C, we have to find the molar specific capacity. Hint, remember the relationship between the smallest and C involves molar mass. Already you know that. Yeah. Okay. Thank you. These are all for today. Okay, thank you. Okay, thank you. Thank you, students. Thank you, teachers. Thank you all. Jai Bharat, Jai Hind, Jai Vidyasati. Thank you all.